All right. Folks, here we go. I believe we're recording this time. All right. So, in what way does the Earth revolve or orbit around the sun? And so we know it goes counterclockwise. We're kind of looking some stuff up with that yesterday. How long does one revolution take? Well, we look at the answer here. It says 1 year is 365 days. Well, actually, 1 year is 365.25 days, hence leap year. Right? Every 4 years, we have to add a day to the calendar to make up for that 0.25 days that it takes for the Earth to go around the sun. And so, this year, hey, you get an extra day of school, lucky you. How long does it take for one rotation as it is spinning on its axis? Well, we talked about that one. One rotation is 24 hours, and we call that a day. How many degrees is the Earth's axis of rotation tilted in relation to its orbit around the sun? And we talked about that, and we looked that up, and we saw that it's 23.5 degrees. So that 23.5 degree tilt really makes a big difference in terms of the way the sun's energy reaches our planet. And so right now, as this is pictured here, the northern hemisphere being the top half of the Earth, if this is my equator, here's my northern hemisphere. And if we look at how the sun's rays are coming in right here, the more direct rays are going to be the ones that are in straight line here. So they're going to hit right about here, right? And then they get weaker and weaker as you go away from that. But straight line right here, northern hemisphere. So if I have more direct sunlight hitting the northern hemisphere, it's going to be summertime. Here's my summer solstice, June 21st, right? So the winter solstice, if I were going to look for that within the orbit of the Earth around the sun, I'd look at the opposite side, right? And so the Earth's tilt makes it so that more sun is hitting the bottom half of the Earth, the southern hemisphere, less of it in the top. Okay, kind of gets spread out as it hits here. It's almost like if you've ever had a magnifying glass and you're trying to focus the beam, you notice that if you don't have that circle, right, that really small circle, you can't burn anything with the light from the sun using magnifying glass. Not that I have any experience with that, mind you. I did get in trouble one time for burning my name into a brand new redwood deck that my parents had put up, and I had to sand it out, old school Mr. Miyagi style, no electric sanders. That was kind of my punishment. So, what percent of the total Earth receives sunlight at any one time? Well, only half of the Earth actually has sunlight at any one time, but because of the tilt at different times of the year, you have more of that half, a bigger portion of that half going to one hemisphere or the other. So if you look here, you got this piece of this half of the pie going to the north and only a little bit in the south, and the same thing here, right? And so daylight hours are the longest here in the summer and shortest in the winter because we're getting less of that light. Now the equinoxes, equal, right? This is times where you're getting roughly the same amount of sunlight, same intensity in both the northern and the southern hemispheres. And so that occurs on these parts of the Earth's orbit. And once again, that's because the tilt isn't making any one hemisphere being closer to or further away from the sun. So here where it's tilted, it's got this part having more of that direct sunlight and this part having, I guess, not further or closer to or further away, but you're getting more or less of the sun's rays. And so here it's equal on the top and the bottom, right? Because the tilt is not making any one part of that get more or less sun, right? And so in spring and March and in the fall and September, you have those equal hours of daylight on September 21st and March 21st. Now, closest to the sun, furthest away from the sun. Closest to the sun, it turns out that by about 5 million kilometers, January 3rd is the time when we are closest to the sun here on this planet. Now, that's a little bit weird, right? We would think being closer to the sun would make you be hotter, right? But our seasons and everything about our seasons doesn't really have much to do with how close we are. It's not really going to affect the intensity as much as that tilt, right? And so our coldest time here in the northern hemisphere is when we're closest to the sun. January 3rd is a pretty cold time of year. July 4th is a pretty warm time of year. But again, it's because of the intensity and the directness of those rays as opposed to how close we are. Now, obviously, if this was a bigger difference, right, percentage-wise, then that would make a bigger difference. But because it's not, it's more about the tilt than it is how close we are. So no, definitely not how close we are affecting seasons. It's all about that tilt, and that's what's going to give you your seasons. Right? All right. The two balanced forces that keep Earth in orbit, right? What's going on here, right? And so this is a little bit misleading. Inertia is not really a force. Inertia is a property of matter based on its mass. And so if you've taken any physical science or physics classes, you know that inertia is an object's resistance to change in motion. And so when the Earth was set moving way back when, along with all of the other celestial bodies in our solar system, they started to move. And as they started to move, they had to pick a path. And if the sun hadn't been there, if the gravitational pull from the sun hadn't been there, they'd have just flown off until the gravity of some other large object had affected them and caused them to either get drawn into that object or cause them to start orbiting. Well, because the sun was there, as the planets and moons and things of that nature started to form, their inertia, which made them want to go off in their own direction, combined with the gravity of the sun, caused them to have these very specific paths, right? If either one of these two things left or was no longer there, then the other one would take over. If the Earth stopped moving in terms of its orbit, then we'd get sucked into the sun. If the gravity of the sun was no longer there, then the Earth would fly off into space, maybe collide with another planet. How about a movie like that where we have to try and figure out how to make up some kind of thing that's going to keep the Earth from colliding into another planet and going off into outer space? All right. Congratulations. Here's the whole thing. Now, you might want to copy some of these things down in a notebook somewhere. Obviously, this will always be available to you, but if you want quick access to it sometime through paper, you may want to go ahead and go through that. So thank you, and peace out.